Okay, guys, so as we begin to start our last and final unit of chemistry for the entire year, which I'm sure you are super excited about, let's make sure that we get our name on our paper and whatever class period you're in. So the first thing we want to do is just kind of review again about temperature. So remember that temperature measures the amount of heat that's in an object, and heat is the amount of kinetic energy in a molecule, right? In our last unit, we talked about how molecules have two types. We have kinetic energy, talking about movement, and we have potential energy, which is stored in the bonds. And a molecule with a large amount of heat is going to be moving quickly. If you think about it this way, if you were walking across the road barefoot, if it was in the middle of summer, you'd be moving very quickly because that ground is very hot. But if it was cold, you could move a little slower. And so that leads us to our next kind of blank in our notes. It says a molecule with a small amount of heat is moving slowly. And so we see that temperature and speed are directly proportional. This means that if you change one of those factors, the other does the same thing. And so we see this because if I increase my temperature, I increase the speed. And vice versa. If I decrease the temperature, I decrease the speed. That's what it means to be directly proportional, and that's a math term that you should have learned in your math classes. So now what we're going to be doing is there's several laws that we're going to learn about, and so the first one is Charles' law. It's named after a guy. Doesn't really matter that you know all about him, but what we have is we have some scenarios here to help us learn about Charles' law. So let's read the first one. It says, Edward is a chemistry student who loves to play soccer. Every afternoon after school, he gets together with his friend Brandon to play soccer outside. One day during the spring, when it was hot in the afternoon and cold in the evenings, he left his soccer ball in the front yard. On the way to the bus stop the next morning, he noticed that his ball had deflated. So there's a few key things there. We want to notice that it's hot in the afternoon and cold in the evenings, and that on the next morning he noticed that his soccer ball had deflated. Okay, so let's look at the next scenario. It says Alexandria is excited about her upcoming 15. On the day of the big party, she moves her big, beautiful balloons to be away from the sunlight coming in from the windows to a corner where there is a vent for the AC. After about after about a couple of hours, she notices that her balloons are getting smaller and starting to deflate. When she puts them back by the window, they inflate again. Okay, so let's notice that when they're by the window, they inflate again. And then when it's by the AC, her balloons are starting to deflate. Okay, and then there's a demo that I want you to watch. It says, describe what happens to the balloon when the flask is heated and when it's cooled down in the ice. So what I want you to do is I want you to pause the video and switch over to the other video in the playlist, or if this is Miss Allison's class that your substitute teacher should have already pulled up, and watch that and then come back to write down what you saw. Okay, so you should have watched that video and seen what happened, and I'm not going to write down what you're supposed to see in case you didn't go watch the video. You actually need to. But what these three scenarios teach us about the relationship between volume and temperature is that volume and temperature are directly proportional. They're similar to temperature and speed in the fact that when you change one thing, it happens. We see that in the fact that when Edward's soccer ball was left outside at night when it was cold, the temperature went down, and so the volume of his ball also went down. It deflated. And Alexandria's balloons deflated when they were near the cold AC, but inflated when they were in the sunlight and their temperature started to rise. And so what this looks like mathematically is that the volume is over temperature, okay, and it's equal to a constant, that's K. And so K is constant, well, is a constant, and that's because the ratio between volume and temperature remains a constant number. It could be 20, it could be 10, it could be 1,000, but the ratio between them always has to be the same. If you increase your temperature, you increase your volume. If you decrease your temperature, you decrease your volume. That's what we learned there. Now, what this allows us to do is be able to determine how much one of these values will change if we change the other one. And so that formula, like this, V1 over T1 equals V2 over T2. And so the ones are the initial values, and twos are the final. So we're going to look at some practice problems for those later. But we want to continue with our conversation about temperature, because this idea of Charles' law really came into a bit of a conundrum to the scientists, because they said, okay, what temperature scale are we going to use? Because first of all, Fahrenheit is only used in 3 countries in the whole world: America, Liberia, and Myanmar. And that's not realistic for scientists. Only 3 countries use it. Majority rules. And so in the last unit, you were introduced to a new unit called Kelvin, which is symbolized by the letter K. And we normally use Celsius or degrees Celsius. So why did we introduce you to that new unit? Well, we introduced it to you because of what we see in Charles' law. And so let's look at these graphs here. What we see is, we know that with Celsius, you can go from, negative 100. Actually, I think the lowest that you can go is negative 273 degrees Celsius. And, you could go up to 1,000. It could be a lot. And so what this shows us with volume and temperature is that a graph of volume and temperature would be a straight line up and to the right. And so that means if I have something at 0 degrees Celsius, then that same spot on my graph, okay, should be 0 liters of volume. Well, that means down here at negative 273 that we should have negative liters. But you can't have a negative volume. You can't have something take up a negative amount of space. It's just scientifically impossible. And so what they decided, and we're going to fill in some of these blanks as we go, that if we have a negative degrees Celsius value, then we would also have a negative volume. And since that doesn't exist, scientists had to adjust, as they're known to do. Hence, Kelvin was born, and by that I mean just the unit. Kelvin was a scientist who it was named after. And what's special about Kelvin is that it is the only temperature scale that we use that has only positive values. So it starts at 0 and goes forth. And actually, a fun little fact is that 0 Kelvin, or OK, as scientists like to joke about, because you would not be OK at 0 Kelvin, is called absolute zero. It's never been reached before, and scientists are actually currently doing a lot of research trying to get molecules to measure at 0 Kelvin. This is when atoms would completely stop moving. It'll be so cold that not even a single atom will be vibrating. And clearly, if you were to be at 0 Kelvin, you would not be okay because your atoms would have long since stopped moving to the point where you'd be dead. But scientists know that cool things could happen, and someone, I'm sure, will win a Nobel Peace Prize. And there's a lot of theories about black holes and 0 Kelvin and things like that. So if you're interested in it, you should do some research. But the important thing is that with Kelvin being our temperature scale here, a positive value will always give us a positive answer for volume. And so the way we convert between Celsius and Kelvin is your Kelvin value is going to be equal to your degrees Celsius, so whatever you have, plus 273. And so that means the opposite is true, is if you want to know the temperature in degrees Celsius, but you have Kelvin, you just take your Kelvin and subtract 273 degrees Celsius. And so that will be how you use to convert. And anytime you're using gases, you have to have the Kelvin unit. Otherwise, your answers are going to be all kinds of crazy. So let's go ahead and look at the third law. This law is called Gay-Lussac's law. And again, that was the last name of a scientist. This law was named after. He did a lot of research in this area. So let's read our scenarios. It says, Angel likes to have a soda in the afternoon, but one summer afternoon he left his can of Coke in his friend's car. Later, he gets an angry phone call from his friend because the can had exploded and sprayed Coke everywhere. Okay, so let's see, it's one summer afternoon, so it's probably hot, and the can explodes. Okay, so that's interesting. And then in our next scenario, it says Yamalex and Andrea were driving to meet Amna at Starbucks to study for their chemistry final. Man, what a good idea that is. When someone rudely cut them off, the brakes were slammed and the tires popped. Okay, so the tires popped. When they took the car to get a new tire, the mechanic said, "This is how you know it is summer. All the tires are popping." Again, it's summer and tires are popping. And for our demo, there's a water and a candle. And again, I want you to pause the video and go watch the water and candle demo. Okay, so you should have watched the video. So let's think about what these scenarios teach us about temperature and pressure. So one thing to keep in mind is that pressure is just force on an area. Okay, and so when we're thinking about the first scenario, the pressure was the soda can, right? It was closed, and so it was put under pressure. And so what we saw was that when it heated up in his friend's car, it exploded. So the temperature increased and the pressure became so high that it popped. And the same thing happened to the tires. And so that means temperature and pressure are also directly proportional. So what you do to one will happen to the other. And so this gives us a formula. It looks very similar to the one for Charles' law, where pressure over temperature is equal to K, this constant. And so if we're looking for how to determine the change, P1, or the first pressure, divided by the first temperature is equal to P2 over P2. where again, 1s are your initial values, 2 is how it changed. And so that leads us to the fourth section, but the third law, Boyle's law. And so let's read our scenario. It says, Madeline's little sister was playing with a balloon when she decided to sit on it to make it smaller. The toddler then became super upset when the balloon popped. Okay, so she wanted to make it smaller and the balloon popped. Okay, now the demo. Explain what happened to the Coke can. Again, pause the video, go watch the demo. It's really fun. And then resume the lesson when you're ready to go. Okay, so there's another activity about what happens to the marshmallow when you pull the syringe out and push it back in. So your teacher should be passing this out for you. Please do not get the marshmallows all stuck in the syringe. It's annoying to clean out. But what I want you to do is I want you to put the marshmallow inside the syringe, inside the, container, put the syringe in, and then put the cap on the end so that you can maintain the pressure in there. And so what I want you to notice is as you pull the syringe out, what happens to the size of the marshmallow and what happens as you push it in. And write down what you observe. And so what we see with this relationship is that pressure and volume do the opposite things. And so that means they are indirectly proportional. So they're indirectly proportional. They do the opposite of each other. So if you increase your pressure, you decrease your volume and vice versa. And so that means that your pressure and your volume are multiplied by each other to get K, our constant. And so what this looks like in our formula is P1 V1 equals P2 V2. And so one thing that we want to move into is just kind of how to solve these types of problems. So I've listed some steps. We've given you a lot of formulas, but guys, it really is super easy. If you look at your periodic table and flip it over the back, there's a rectangle box at the bottom, and it has all of the formulas in it. So you do not have to memorize them. You just have to know how to use them. And so one thing we want to say is that pressure can have a couple different units, and you need to be familiar with them. The most common one you'll see is atmospheres, but you might also see pascals, which is abbreviated as PA, millimeters of mercury, PSI, which is pounds per square inch, or torr. And then with volume, you're always going to be using the units of liters. And then temperature, you're going to see Celsius and Kelvin. But remember that all of your answers need to be in Kelvin for the gas laws. And so what you'll do is you'll read through the problem and you'll label each one as being P, V, or T. Is it pressure, volume, or temperature? And then you'll look at the back of the periodic table and you choose the formula that only has those letters. So if you only have a volume and temperature, then only pick the formula that has volume and temperature in it. If you have temperature, you need to change degrees Celsius to Kelvin, plug the numbers into the formula, and solve for the missing letter. And just as an FYI, if you see the phrase or the letters STP, that means standard temperature and pressure. So this just means most conditions in a research laboratory at standard temperature and pressure is always going to be referring to 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere of pressure. So it's important to know that if they say STP in the problem, they've given you a temperature and a pressure at the same time. So why don't we go ahead and look at some practice for this. So number 1 says if a gas occupies 2.60 liters at a pressure of 1.00 atmospheres, what will be its volume at a pressure of 3.50 atmospheres? So we're going to follow the instructions and steps. So it says to label each unit as being pressure, volume, or temperature. Well, if I look at 2.60 liters, I see liters, and I know that that means volume. And then I see 1.00 atmospheres. That means pressure. And then again, I see 3.50 atmospheres, so that again means pressure. So what I'm going to do is I'm going to go ahead and label these as V1, P1, and P2, because I know that if I only have volume and pressure, when I look at the back of my periodic table, the formula I'm going to be using is V1, P1 equals V2, P2. So my second volume is what I'm going to be looking for. But I know that this 2.60 liters is my first volume because it's the first one mentioned in the problem. That's how I like to decide on it. And then here it says that this volume is at a pressure. And so that means that these two things here are connected. And if they're connected and this is V1, then 1.00 atmospheres has to be P1. And 3.50 must be P2 because that's what it changes to. And so if we plug our numbers that we have into our formula, we see that V1 is 2.60 liters, P1 is 1.00 atmospheres, and both of those multiplied together are equal to V2, which we do not know, so I'm going to leave it as V2, times P2, which is 3.50 atmospheres. And so in order to solve for V2, I'm going to divide by 3.50 atmospheres on both sides of my equation. And this will allow for my units to cancel and things of that nature. So this cancels out on this side, and it leaves V2 all by itself, which is excellent. And then on the right side, we see that atmospheres cancel out with atmospheres. And when I multiply these together, we're going to have 2.60 times 1.00 divided by 3.50, and that gives us 0.743 liters. And I know it's liters because that is the only unit that did not cancel out. So what I want you to do is I want you to go ahead and I want you to try the other ones, keeping in mind that with these next ones we see that we have 27 degrees Celsius, 132 degrees Celsius. So it's going to be important to remember that you add 273 in order to get the correct Kelvin temperature, which this would be 300 Kelvin. So remember to always convert to Kelvin, and if you want to be able to check your answers, you can check your answers with either Miss Nichols or your current chemistry teacher. If you're in Miss Allison's class especially, your teacher has the answer key. And we will talk about the ideal gas law in the next video on Wednesday.